Good afternoon, America. Today, I'm here with the Moonlight Marauders after they proudly participated in the NASA App Development Challenge. Their mission? To develop an app that simulates the flight path of the Artemis 2 rocket, paving the way for humanity to return to the moon. Now, let's meet the great minds behind the app.
Well, first, thank you so much for having us on. And I guess let's start at the beginning.
So tell me, how did you and your team develop this app?
Well, before diving into development, we knew we needed a proper roadmap. Our first step was understanding the challenge and visualizing our end product. We together brainstormed and broke down the challenge into different components: animation, visualization, physics, calculations, etc. We then began storyboarding. It allowed us to map out our ideas and design an app that both prioritized usability and functionality. We envisioned a tool that merged real-time data with visualization and detailed mission metrics.
To refine our approach, we sought external guidance. A Honeywell aerospace engineer, who we knew through student connections, who builds simulations for airplanes, highlighted the importance of separating data calculations from visualization, a strategy we adopted from the outset.
So, why don't you go ahead and show us what your code looks like?
Sure, it's right here. With our plan in place, we knew what our first step was. We needed to use the raw data provided to generate additional information in the data sheet. We used Python as a team as we were mostly new to collaborative coding, so we wanted to use a more accessible programming language. Using Python libraries such as Pandas and NumPy, we calculated key metrics such as resultant vectors, distances, and the link budget. This posed a huge challenge as many of us were new to multi-file program structures. To overcome this, we divided tasks into smaller functions, allowing each member to develop their own program while learning Python. By collaborating and supporting each other, we built our skills and completed the foundational calculations, which form the backbone of our app's functionality.
So, how did you guys go about formatting and developing your app?
Well, while the backend team handled the data, a few members explored the visualization tools. Our goal was to create an interactive interface that made the Artemis 2 flight path really come alive. So, the PyQt5 Python library emerged as the best choice for our user interface. While Matplotlib allowed us to create dynamic 3D visualizations, together these tools formed the foundation of our GUI.
Over the next several weeks, we worked tirelessly to bring our vision to life. Each feature required careful planning and execution. Let's walk you through the features step by step. Over on the left, we have our visualization of the Artemis 2's flight path. As you can see, we have the Earth and the Moon. This visualization is fully interactable. You can rotate it, pan it around, reset the layout, or you can even zoom in and out. In addition to this, you can hover over a point and find various mission metrics, such as time and the mission status. We also added an animation that shows the Artemis 2's flight path in real time, showing how it evolves dynamically. We've also implemented several animation controls. This includes things such as pausing the simulation and restarting it. In addition to this, we've also added a button that allows you to toggle the Moon and Earth on and off. This is because having them visible actually slowed down the animation greatly. So we decided to adapt to this by simply allowing the user to toggle it on and off. All the animations, plotting, and data visualization were built using Matplotlib, with a dedicated team member handling this portion.
Now let's discuss color coding. Pressing this button opens the color key. As you can see, numerical metrics like resultant velocity and distances are color-coded for easy interpretation. Green indicates an increasing value, and red indicates a decreasing value. Mission stages are also color-coded. Green is when orbiting Earth, purple when on the way to the Moon, brown when returning to Earth, and orange upon re-entry. Pink is for landing and descent. Now let's look at the antenna connectivity.
The number of connected antennas is labeled and paired with this color box indicator right here. Yellow's for when there's only 2 satellites connected, red's for when there's less than 2 satellites connected, and green is for when there's 2 or more or 3 or more satellites connected.
We wrote dictates the color for app and updates metrics labels based on the index. We gradually added more to it as we needed to adapt other features. So having one function that can be called anywhere else in the program made the programming easier.
For us, the main event was link budget and leased antenna prioritizations. As you run this animation, you can see the prioritization of satellites based on the link budget. The table shows us a list of antennas prioritized by which one can provide the best connection at any given moment. We calculated the link budget for every antenna throughout the simulation, adding 4 columns to the datasheet for each respective satellite. At any given moment, we sorted the satellites by their corresponding link budget, and thus we have this priority table. But finding the table with the fewest antenna changes was definitely a challenge for us. Let me explain why this is harder than we thought. Take this example of satellite connection data. WPSA is clearly prioritized first because it is the only connected antenna from times 1 to 2. However, by time 6, WPSA will be disconnected and we must update the top prioritized satellite. How can the program predict that DS34 will last longer if it reads the file row by row? It was only after coming together and presenting the problem to each other that the solution dawned on us. We realized that we could add 4 extra rows to the datasheet to show how many future moments each satellite would stay connected. At time 6, for example, this revealed DS34 as the best choice, with 4 more moments of connection compared to DS24's 3 moments. DS34 would rank second, while the other satellites are deprioritized due to no future connection. Based on these values, we implemented an algorithm that prioritizes the satellite which had the top priority at the last moment if it was still connected, while the rest of the satellites are sorted by their future connection length. And here's the result. Let me now show you this table in action. I simply toggled to switch to the prioritization by least antenna changes.
Another feature in our app that posed a challenge for us was total distance covered. To gain some guidance on this challenge, we reached out to someone at Arizona State University, an astrophysics PhD student who we knew through Student Connection. He explained to us that we could simply add up the magnitudes of the differences of the position vectors throughout the simulation. So point to point, we simply grabbed and summed up the distances to finally get the total distance covered. We applied his explanation of what the mathematics would look like, and with this code, we added a column to the datasheet showing total distance covered.
So, how did you guys engage with your community?
Well, throughout this challenge, we had 2 community engagement events. In November, we presented the NASA ADC App Challenge in a slideshow and our app to the CTE software and development classes, inspiring interest in the competition and possibly attracting new club members. We also promoted the Quantum Day by organizing activities in computer science classes where students collaborated on interactive games. Now, many are excited about Quantum Day next year.
The NASA App Development Challenge has been an extraordinary journey of growth and innovation. We as a team learned object-oriented programming, Python data analysis and visualization, and physics. But more importantly, we learned how to collaborate in a structured and organized way, adapting to constraints, overcoming obstacles, and so much more. We truly felt like NASA engineers.
Thank you, NASA, for this amazing opportunity.
Moonlight Marauders, out!